a big formula in the reading. Y dot u over u dot u times u is called the orthogonal projection. Orthogonal projection. Okay. If x dot y equals x dot z equals y dot z all equals 0, and the length of y and the length of x and the length of z are all 1, what do we call the set x, y, z? No. Orthonormal. It's orthogonal because everything is orthogonal to everything else. And the norm, or the length of every vector, is 1, so we call this orthonormal. Okay. If an n by n matrix U has orthogonal columns, if and only if what? You got it. They have to be, its columns have to be orthogonal and all have a norm of 1, a length of 1 to be orthonormal. Yeah. We'll go through some of the notes on the reading. So a set is said to be orthogonal. The whole set is orthogonal if every pair of distinct vectors in the set is orthogonal. So any two pairs of vectors you pick out from the set are orthogonal to each other. And if S is an orthogonal set of non-zero vectors in Rn, then S is linearly independent. That's a theorem. Yeah. Another definition, an orthogonal basis is a basis that is also an orthogonal set. Okay. So you all know what a basis is already. Right? It's just a linearly independent set that spans the space. Okay, so it's a linearly independent spanning set, and it's an orthogonal set. We call that an orthogonal basis. All right, so if S is an orthogonal basis for a subspace W, then any y in W can be written as a linear combination of vectors in S, right? That's what a basis is. It's the smallest set of things that you can use to build every element of the set. Okay, so we usually figure out, right? So I can pick any vector y and I can write it as a linear combination of the vectors in the basis. Usually we find the weights by setting up a system of equations and solving, right? Augment, row reduce, and you have the weights. But we have another way of finding weights now. When you have an orthogonal basis, right? This only works if the basis is orthogonal. You can find each weight C sub j by doing y dot u sub j over u sub j dot u sub j. So you do that for each weight. Like if you wanted to find the first weight, C1 would be y dotted with u1 over u1 dot u1. Y is given, right? You're given a y and you're trying to write it as a linear combination of vectors in the basis. So y is given, and the u1 is the first vector in the basis set. We'll do an example. It'll be clear, I think. All right. So here's what I think this is. I think that this is the hardest part of the reading in this section. So if you're given a non-zero vector u in Rn, then for any vector y in Rn, you can decompose it into the sum of two vectors. One's going to be a scalar multiple of u that you were given, and the other is orthogonal to u. So we typically, we do this a lot in like physics 1. I'm sure you did this a lot, where like you take a force that's denoted with a vector, like call this, I don't know, 5, 4, right? And you break it down into its horizontal and its vertical components. So you draw a perpendicular and you say that's 5, and then you go over here and say the other part is 4, right? All right, so the thing is, you can do this. We usually have this as the x-axis. And so we're always dropping a perpendicular from the vector to the x-axis. But we could use any other line other than the x-axis and do an analogous process. Drop a perpendicular from your vector to any other line through the origin. Okay, so that's what this picture is here. So here I've got some vector y, right? This is my given vector y. And I'm given a vector u, so I can draw a line through u, right? And I can break it down into the force in the direction of u and a force perpendicular to u. So you just draw perpendicular to u, and then this point right here, that's called y hat. Okay? That's the orthogonal projection of y onto u. And then this little guy here is called z, y minus y hat. It's like the y part. Like when we did it over here, the 4, that would be your z. This would be your y hat. This would be your z. Why would you not use I, j, and k? We're going to get there when we do the least squares problem in 6.5. Yeah, and it's hard to motivate why, but you'll see it very soon. So that's how we break it down, right? So the same process can be applied more generally to any dimension. We don't always just use I and j to break things down. You can break it down any way you want. So we have a formula. This guy calculates y hat, which is the orthogonal projection of y onto u. Sometimes we say it's the orthogonal projection of y onto L because it's actually a line in the direction of u. We call L that whole line, the span of u. Z you always calculate by just doing y minus y hat. And if you wanted to know the distance from y to L, and this is what's going to be key later on in the section, how far apart y and y hat are is just the length of y minus y hat. Okay, a couple more definitions. A set is an orthonormal set if it's an orthogonal set of unit vectors. So everything's orthogonal to everything else, and all of the vectors have length 1. An orthonormal basis, right? It's an orthogonal basis, which we already discussed, where all the vectors have length 1. So the standard basis for Rn is an example of an orthonormal basis. Like for R2, it would be 1, 0, and 0, 1. Those two vectors are orthogonal to each other, and they're unit vectors, so they form an orthonormal basis for R2. An M by N matrix U has orthonormal columns if U transpose times U is the identity. And then orthonormal, a matrix that has orthonormal columns has some special properties. You'll verify that these are true in your activities. So I'll just let you read about that later. And then that too will come up later in the activities. All right, so let's look at some examples. So we've got 3 vectors here, U1, U2, U3, and then a 4th vector called X. So I want to show that U1, U2, and U3 is an orthogonal basis for R3. Okay, so I have to show it's a basis, which means I have to show it spans R3 and it's linearly independent. And then I have to show that all the vectors are orthogonal to each other. Okay, so let's look at basis, right? I got to show 2 things. Linearly independent and spans R3 because it has to be a basis for R3. All right, so how do I show those 2 things? We could put them in a matrix, row reduce. What am I looking for? Yeah, a pivot in every column for linearly independent, a pivot in every row for spanning. And then, so I should get the identity matrix, right? So I'm just gonna, this is like a good reminder for lots of things we've talked about. So I'm just gonna write it all out. Pivot in every column. Pivot in every row. All right, so let's go ahead and verify that. 1, 0, 1, negative 1, 4, 1, and 2, 1, negative 2. REF that in your calculator, and you do get 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so check and check. So we know that this is a basis. The last thing we have to show is that it's an orthogonal basis is that every vector has to be orthogonal to every other vector in the set. How do you show two vectors are orthogonal? Dot product, and you should get the 0 vector. Yep. All right, so U1 dotted with U2. So this is 1, 0, 1 dotted with -1, 4, 1. So that should be -1 plus 0 plus 1 is 0. Okay, so check. U1 is orthogonal to U2. Yeah. No. You have to do every possible combination of vectors. Yeah. Yeah, I wouldn't give you 10 vectors though. So I'm going to dot U1 with U3, 2, 1, -2. So I get 2 plus 0 plus -2, 0. Check. And then finally U1 dotted with U3. Oops, that was U1, U2 dotted with U3. So I have -2 plus 4 plus -2 is 0. Check. Okay. So this tells me these three dot products tells me that U1, U2, U3 is an orthogonal set. So we showed it's a basis, we showed it's an orthogonal set, therefore it's an orthogonal basis. If I normalized the vectors, what does normalize mean? Make them unit vectors. If you make them all unit vectors, that would produce what kind of a basis? Orthonormal. Right? It's already orthogonal. If you make all the vectors normal by making them length 1, now we have an orthonormal basis. Yep. Oh, yeah. Okay, so still the same problem, still using U1, U2, and U3, right? Because the set U1, U2, and U3 is an orthonormal basis, sorry, it's an orthogonal basis for R3, that means any vector in R3 I should be able to write as a linear combination of the vectors in that basis. Right, so I should be able to write X as C1 U1 plus C2 U2 plus C3 U3, based on the fact that U1, U2, U3 is a basis for R3. No, because you'd get different C's. Yeah, so I want to write X as, I want to figure out what C's do I put on the basis vectors. Yep. C is just a scalar, yep. So normally I would figure this out by, I would just be saying, okay, well, I want to figure out what C's I put on 1, 0, 1, -1, 4, 1, 2, 1, -2. What C's do I multiply by to get the vector X, 8, -4, -3? Okay. Yeah, you just augment and row reduce. Okay, so I'm going to do this two ways. The way we already know how to do it is to augment okay, and we get 1, 0, 0, 0, 1, 0, 0, 0, 1, 5 halves, -3 halves, 2. So those are the weights. So that's C1, C2, and C3, right? Okay, so that's the one way to do it. We already knew how to do that. We're going to use our special formula now to do it another way. Well, there's a reason I'm showing you another way. It's going to come in handy. It's not just to have another method that you'll forget. Okay. All right, so we have this formula that the weight, C sub j, is y dot u sub j over u sub j dot u sub j. Okay. All right, so C1 should be y, or in our case, x, because x is the vector I'm trying to write as a linear combination of the u's. Okay. So I'm going to change that to an x. So this is x dotted with u1, the first vector in the basis, over u1 dot u1. Okay, so this should be 8, -4, -3, dotted with the first vector in the basis is 1, 0, 1, over 1, 0, 1, dotted with 1, 0, 1. Okay, so my numerator should come out to 8 minus 3 is 5. And my denominator comes out to 1 plus 1 is 2, 5 halves. That's what I got for C1 earlier. Yeah, I only used U1 to calculate it. Yeah. It only works because it's an orthogonal basis, right? So it's kind of like if you had 1, 0, 0, 0, 1, 0, and 0, 0, 1. Only one of the vectors matters. Yeah, is going to contribute. Yep. Okay, so let's see. If I calculate C2, that would be x times u2 over u2 dot u2. It's going to come out to -3 halves. We know that. Yep. All right, so x, we've got 8, -4, -3, dotted with the second vector in my basis, which is -1, 4, 1, over u2 dotted with u2. So -1, 4, 1, dotted with -1, 4, 1. So I get -8 minus 16 minus 3, which is -27, over 1 plus 16 plus 1 is 18, and that reduces to -3 halves. Okay, and one more, C3 is going to come out to 18 over 9, which is 2. All right, so it's just another way of finding the weights. Like, what weights do you put on a basis to get a given vector? And remember, this trick only works if you have an orthogonal basis. Okay, number 2. This is what I think is tricky. So we're going to draw it. We're going to draw it all out before we even use the formulas to calculate stuff. So I want to compute the orthogonal projection of 1, 7 onto the line through u, which is -4, 2, and the origin. So I've got a point 1, 7. I'll plot it. 1, 1, 2, 3, 4, 5, 6, 7. I'm sorry you don't have a grid. I just added this right before class. You can just sketch it in if you want. All right, so I've got the 0.17, that's y. So I'm going to label it y. And then I have a line through -4, 2. So I'm going to plot -4, 2. 1, 2, 3, 4, 1, 2. And I'm going to draw that line through that point in the origin. Oh, God, that was terrible. All right, that's better. That's U right there. All right, so I'm trying to come up with, I want to break y down into the sum of two vectors. One is going to be a vector in the direction of u. So u is like, picture u as like the new x-axis. So you want a vector in the direction of u, and then we also want the perpendicular vector, which is like the new y-axis. All right, so just drop a perpendicular from y onto u. That is y hat. That's what we're looking for. That's the orthogonal projection of y onto u. Okay, so this vector in the span of u, we call that y hat. And the other vector orthogonal to u, we call that z. Okay, so z is like the new y-axis. It's the vector perpendicular to the new x-axis and through the origin. So I am going to draw a perpendicular here. That's like my new y-axis, new x, new y. And so this vector right here that has the same length as my y, right, from y to u, this is my z. So you can see that I've created a parallelogram, right? Y hat plus z, right? Remember, how do you add vectors? Tip to tail, yeah. So y plus z, y hat plus z gets you to y. That's what we're trying to do, right? If you moved y hat up to the tip of z, it's going to land you back at y. So that's my goal. I want to rewrite y as y hat plus z. All right, so let's just estimate from my picture. Y hat, what does that point look like? Y hat, negative, the first, negative 3, 2. Oh, I drew that terribly. It is, yeah, so based on this picture, it looks like negative 3, 2. We're going to calculate it in just a minute. Okay. And then z, what does z look like? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Z is a vector, yeah. Yes. Thank you. All right, so those are just our estimates, y hat and z. If I add y hat and z together right now, do I get 1, 7? No, right? That's my goal. I want to come up with a y hat and z that are orthogonal to each other, perpendicular, like the new x and y axis. So they have to be orthogonal, and they have to add up to 1, 7. Right now, they don't add up to 1, 7. They add up to 2, 7, which is pretty close, right? So our estimate based on the picture is pretty close. And if I dot product them, do I get 0? No, I get negative 15 plus 10. I get negative 5, right? So they're not orthogonal either. But that's because this is a terrible picture. I'm terrible at drawing these things. So I'm gonna do all the calculations and figure out what y hat and z really have to be. All right, so y hat we calculate by doing y dot u over u dot u times u. These are all vectors. So y is the 0.17. U we were given, it was negative 4, 2. Yeah, negative 4, 2. Over negative 4, 2. Also dotted with negative 4, 2. So this fraction should come out to a scalar, right? And then I'm going to multiply it by the vector negative 4, 2. Okay, so this first dot product, I get negative 4 plus 14, which is 10. And then the dot product on the bottom, I get 16 plus 4 is 20. So that's 1/2 times the vector -4, 2. So I get -2, 1. So that's my real y hat, -2, 1. Yeah, because if I put it on the top, it looks like a dot product, right? It's just, I mean, I could put it on the top, that would be fine, but you just have to be really clear that this is a dot product, and this is a scalar times a vector. Yeah. So I put it over here just to be really clear that there's no dot there. Yeah. Yeah. All right, so then z, right? Z we just calculate by doing y minus y hat. Okay, so y is 1, 7. Oops. Minus y hat, which we just found, -2, 1. So I get 3, 6. Okay, so those are pretty close to my estimates. My estimate was -3, 2, right? And 3, 5, or 5, 5, right? So my picture was apparently terrible, but these are, at least they're like in the right directions, right? Negative, positive, positive, positive. So let's check, right? My whole goal was that I was trying to write y as the sum of y hat and z. So does the sum of these two add up to 1, 7? 1, 7, yes. Check. Okay, so I've written y as a sum of these two vectors. Now I'm hoping that they are orthogonal to each other. Okay, so -2, 1 dotted with 3, 6. And I get -6 plus 6 is 0. Orthogonal. So these are like my new axes. -2, 1 is in the direction of u, right? Because u was -4, 2. So the question said, rewrite your vector 1, 7 as the sum of two vectors, one in the direction of u and one orthogonal to u. Okay, so this vector is in the direction of u, meaning on the line that is the span of u. And this one is orthogonal to u. That looks like a hat, it's just an arrow. Does that kind of make sense what we're doing? We're making a new x-axis and y-axis and breaking our vector of forces down into the direction of u and a perpendicular to u. Okay, that's it. You can work on some now on your own.